So far, most of the problems we've looked at have been pretty straightforward, dare I say simple problems. But one way we can make our problems a little more complicated is to introduce multiple events. So let's look at what that means and how we deal with it. So let me just remind you, the kinematic equations only work when the acceleration is constant. So the a in our equations has to have one single value. If an object has an acceleration that changes, for example, maybe an object accelerates at 2 meters per second for 5 seconds, and then the acceleration changes to 10 meters per second for a certain amount of time. You have to break the problem into pieces. And each chunk or each piece is when for one single value of the acceleration. So we're going to use a motion information table that we practiced last week to organize the different events. So what we're going to do is every time the acceleration changes, we'll have a new event. So you can imagine there's like an event, the first event for one single acceleration, and then you need another event because the acceleration changes, and then you can have another acceleration after that. So that sounds weird, but we're going to do it. Okay. So here's a problem. If you want, what I want you to do is press pause, read through it, and try to think about what different events are happening. And remember, every time the acceleration changes, you need there to be an event that says the acceleration is changing right now. Okay, so press pause, see if you can identify how many events we have here, and think of if you can name these events. Okay, so what I would do is I would say event 0, because we're always going to start with 0 in physics. Event 0 is when the car starts, okay, from rest. Now, it has this acceleration, 7 meters per second. But then the car coasts. And when we say coasts, we mean it's not accelerating, it's traveling with a constant velocity. The acceleration is 0. So I need to have an event to break things up, because from the time it starts till this point when it starts to coast, my acceleration is 7. But now, from the time I start to coast until I start to brake, then because it's slowing down, oops, sorry, it's going to slow down. From here to here, the acceleration is 0. And then from the time we start to brake until we actually stop and come to rest, I'm going to have this acceleration of 2 meters per second squared. So you see I have 4 different events here. Each of the events happens when my acceleration goes from one value to another value. That's why I put an event there. So I'm just going to warn you, picking your events is one of the hardest parts of these types of problems. Choosing your events is very difficult. If you can be really careful and pay attention to what the acceleration is doing, it won't be as hard to choose your event, and the problem will be a lot easier for you. So let's show our complete motion information table. And what you remember, I have my events are going across the top, and then in the coming down, I have all the variables that apply to that event. So I have t0, that's the time when we start, x0, that's our position when the car starts, v0 is the velocity when the car starts. Here I have t1, x1, and v1. Those correspond to those variables when the car starts to coast. Like what time is it when the car starts to coast? What's the x position? What's the velocity? Same for the time 2, and then event 3. And then in between here I have a delta t. Delta t is like what takes us from 0 to 1. So this would be like t1 minus t0. Delta x would be like x1 minus x0. And a, what's the acceleration that I have while I go from event 0 to event 1? So this is kind of just filled out blank. And now what we can do is go through the problem and look at all these values that I've been given and try to fill in as many numbers as we can. Okay? So in the past, when you drew a motion information table, you just had like these 3 columns. But now that we have multiple events, we have lots and lots of columns. So we can always say that we start at t equals 0, so that's fine. And we can say we can put our origin wherever we want. So let's say we're starting at x equals 0. They tell us the car accelerates from rest. That means that initial velocity there is 0. We know that it accelerates for 6 seconds. So it's going to have this acceleration for 6 seconds. So delta t here is going to be 6. I don't know delta x, but my acceleration is 7 meters per second squared. And let's keep going here. Well, if t0 was 0 and delta t is 6, so it takes 6 seconds to go from here to here. This is also going to be 6 seconds. I don't know x1. I don't know v1. We coast for 4 seconds, so this should be 4. I don't know my change in my x position, my displacement, but I do know what my acceleration is here is. If we're coasting, we're staying at the same velocity. That means my acceleration is 0. So I'm going to plug in a 0 there. Now I want to know what time is it when we start to brake. Well, if we started to coast at 6 seconds and we coast for a total of 4 seconds, the time over here should be 10 seconds. And I don't know any of this. I don't know how long it takes us to slow down, but I do know that acceleration, and let's be careful here, we're slowing down at this rate of 2 meters per second squared. Well, I've already kind of assumed that the car was traveling in the positive direction because I give it this positive acceleration, so that's positive there. So when we're slowing down, I want it to be the opposite direction, so I'm going to make this negative, and that's going to be negative 2 meters per second squared. I don't know what time it is when we stop. I don't know our position when we stop, but I do know my velocity. What's the velocity when we come to rest? Well, it's 0. Now that we've filled out as many numbers as we can start to answer the questions they're asking. First, what's the maximum velocity of the car? Okay, so to figure out the maximum velocity of the car, first we need to kind of think about where are we looking on our table. And for this, you really need to kind of understand what's happening conceptually. So I'm going to think, okay, a car is starting from rest and it's accelerating for 6 seconds, and then it stops accelerating after that, and then it slows down. So this velocity here is going to be the biggest velocity that it ever has. So I want to know what is v1. So how am I going to figure out v1? Well, I'm going to focus on this side of the table, and when I do that, everything in this column here is like the initial, and everything in this column here is like the final. So if you look back at your kinematic equations, v1 is really like v final. So look at those kinematic equations that Spider-Man told you to write down. Anything that has v final, that might be something we are going to maybe use that equation. So let's look at what variables of our kinematic variables do we know, and I'm just focusing on what's in this red box. I know delta x. I know v initial because this column is like my initial. So I know delta t is what I know. V initial and a. That's 3 variables. That means I know enough information to solve for this 4th variable, which will be v final. So when we look at the variables that we know a delta t, we know an acceleration, we know a v initial, and we want to solve for v final. So now I'm going to look at my list of equations, and I'm going to choose the equation that involves these 4 variables, and that equation is v final equals v initial plus a delta t. So now I can plug in the values that I have for those variables, and I can solve for v final. So v final in this red block is what v1 is equal to. So now I can put this into my table, and maybe that's going to be helpful. Well, it definitely answers this part of the question. What's the maximum velocity? 42 meters per second. Now we also know that we don't even have to do math. Since the acceleration here is 0, this should also be 42 meters per second. So let's just put that in there because that might help us later. So now let's look at solving the second part, the second question. What is the car's total displacement? Where is that on the table? Well, if I could know the value of x3, since I started eventually in the beginning at x equals 0, if I could know this value x3, that would be my displacement. So I want to know what x3 is. So you might think, okay, let's first look at this section here because that's where x3 is. Well, here I know in this column this would be v initial. I know v initial, I know a, I know v final. So you might think, okay, that's enough. There's 3 variables that could let us calculate delta x, but I don't know what x2 is. So how could I figure out x3 if I don't know x2? Because delta x is just the difference between x3 and x2. So I can't get it right away. So maybe we say, okay, let's try to figure out what x2 is. Let's try to look at this region here. In that case, this would be my initial. This would be my final. I know a v initial, I know a v final, I know a delta t, I know a, I know all these things. That is enough to calculate delta x. But again, if I don't know what x1 is, I won't be able to solve for x2. So really, what we need to do is first find x1. I need to figure out this value here. So I'm going to look at a part of my table where I have the most numbers filled in, and that's over here. and I'm going to say, how can I figure out x1? Well, the variable that's going to let me calculate x1 is actually delta x. This is a variable that shows up in my kinematic equations. If I can figure out delta x, which is just x1 minus x0, I'll know what x1 is. Then we can go back to the other ones. Okay, so let's do that. We're going to find x1. Okay, so the variable I'm trying to solve for is delta x. Why did I not say the variable I'm trying to solve for is x1? Because delta x shows up in our kinematic equations, and this is going to let me get to x1. So the variable I'm trying to solve for is delta x. And what else do I know? I know my acceleration, I know v initial, I know v final, I also know delta t, so I could use pretty much any equation as long as it has delta x in it. I'll use my acceleration, v initial, and v final. And then if I choose the equation that involves these four variables, this is the one I use. V final squared equals v initial squared plus 2a delta x. Here I've plugged in all the values, and then I solve for delta x is 126 meters. So this is 126 meters here. And now at this point, you can probably just really easily figure out x1 is also 126 meters. But just to be extra formal, we can say delta x is equal to x1 minus x0. We just solved that delta x was 126. I'm trying to figure out what x1 is, and x0 we already said was 0 meters. So that gives me x1 is 126 meters. Okay, so I can plug that in here. There we go. Now let's move back to trying to solve for x2. So to solve for x2, I'm going to pick two columns that have x2 in it. I could either do this one, or I could do these ones. Let's do these ones because I have more information here now. I filled in something else. So at this point, I want to know delta x because that's going to help me get to x2. I know v initial, delta t, and a. Let's say we use those variables. So I want to know delta x, I know a, I know v initial, I know delta t. I'm going to choose the kinematic equation that involves those four variables. And now I plug in for v initial, delta t, a, and delta t, and I find that delta x equals 168 meters. So that's just delta x, that's just this piece. And it might be easy for you to think, okay, we started off at 126 meters, we have a displacement of 168, that might help you figure out pretty easily what x2 is. But if you want to do it formally and slowly, we can say delta x is x2 minus x1. We can plug in for what we just found for delta x, plug in for x1, and we are able to solve for x2. So that goes here. Great. Now we can finally move back to here, and we can finally figure out what x3 is based on the fact that we know what our delta x is. So I want to know delta x. At this point I know a, and I know v initial. Remember, because for this thing I've colored in green, this column is the initial value. This column has the final values. So v initial is 42 meters per second. V final from this column is 0. I choose the equation that involves these four variables. It's this one. I plug in all the values that I know. That 43 is just the slide number, sorry. And we find out our delta x is 441 meters. That's our displacement as we go from event 2 to event 3. We have this much displacement. That's not our position though, that's our displacement. If I want the actual position, I can say the displacement is equal to x3 minus x2, and I plug in for x2 and the displacement, and I finally find x3 is 735 meters. And that is the total displacement because we started at x equals 0, we end up at x equals 735. That means our total displacement is 735 meters.